All right, we are live. Oh, okay, Zoom is mad that I'm muted. I'll just unmute real quick. Okay. Oops. All right. Oh shoot. Okay. Never mind. I do need to be muted on Zoom. Hopefully it'll stop giving me this alert. All right. So, actually, here maybe I can just. Okay, no, it looks like it stopped. If it starts again, I think I know how to fix it. All right. Anyway, so today was why's my screen so dark? Oh, okay, cool. Let's see. Sorry, just fixing a few minor audio issues. All right, there we go. Okay, so today was Codeforces Round 738 and also CodeChef Starters 8. So the CodeChef contest has about half an hour left, and so I'm going to start by going over the problems from the Codeforces round, and then by the time we finish with that, CodeChef should be over, and so then I will go over the problems from that contest too. So 2 contests today, lots of problems to get through. So let's go ahead and get right to it. Oh, and Codeforces is unavailable. That's great. All right, well, here, let me just pull them up on M2. Okay. So there are also a couple of interesting strategic decisions that I made throughout this round, especially as I approached problems D and E. So I'll talk about those later. But for now, let's start by discussing A. So we're given a sequence A of length n, and in each operation, we can select an arbitrary interval from L to R. And for all for all values I from 0 to R minus L, we can replace A sub L plus I with A sub L plus I and A sub R plus I, where AND is the bitwise AND operation. And we can do this as many times as we want. We want to minimize the maximum value in the sequence. All right. So I actually solved this problem without really reading or thinking closely about what this interval or what this operation meant. I just kind of read the problem and then conjectured that the answer was going to be the bitwise AND of all the elements of the array, and I saw that matched the sample cases, and that turned out to be correct. But let's go through how you actually solve this problem. So, in general, what you should be thinking here is that so let's let x is the bitwise AND of all the elements, so a of 0 and a of 1 and up to a of n minus 1. So the claim here is that the answer is x. Now, first of all, we should prove, now what we need to do is we need to first prove that we can actually get to x, that it's actually possible to make the maximum value x. And secondly, we need to prove that we can never get a lower maximum value. And the second half of the proof is easier, because realize that x is a submask of every a sub I. And the idea is that if x is that wherever a sub I has zeros, because of the definition of bitwise AND, x is also going to have zeros there. And so all of the ones in x have to also be ones in a sub I, because the ones in x are at the positions where we have ones in all the a sub I. So x is a submask of every a sub I. And so the result is that whenever we replace this element with this element, x is going to be a submask of both of these. And so that means that x is going to be a submask of this. And so essentially, this never changes when we perform an operation. And the formal term for this sort of situation is called an invariant. The invariant here is that no matter what we do, x is always going to be a submask of all of the a sub I, and the reason is that performing these bitwise ANDs is that if x is a submask of 2 numbers, then it's still going to be a submask of their bitwise AND. Oh, sorry, I'm seeing some questions. What is a submask? So basically, a submask is a let's see, what's the easiest way to explain this? So if we're looking at a number in binary, let's say, I don't know, let's call this number n, and let's say it's like 1011. A submask of n is any number where the positions of where whenever our new number has a 1, n is also going to have a 1. And so for example, 1000 is a submask because of 1011, because the position of because when we have a 1 in the submask, we have a 1 in the original number. And likewise, when we have and likewise 0011 is a submask, and 1011 is a submask of itself. But 0100 is not a submask of 1011 because there's a 1 in the second position of the submask, but not in the second position of the original number. Okay. So okay. So this shows that the answer, or that a sub I is always going to be at least x for all I. But I think the more interesting part of this problem is to figure out how can we achieve x. That is, how can we make the maximum value in the array equal to x? And the way I do the way I do this is as follows. What I'm going to do is first I'm going to select the elements 1, 2, 1, 3, the elements 1, 2, 1, 3, 1, 4, 1, 5, all the way up to 1n. And what that does is, and what that's going to do is it's going to make a of 1 equal to x. And the idea here is when we do 1, 2, then if we take I to be 0, then that's going to replace a of 1 with a of 1 and a of 2. And then when we do 1, 3, we're going to AND the result with a of r minus 0, which is 3 minus 0, which is 3. So after performing 1, 3, it's ANDed with a of 3. And so on, all the way up until we reach n. And now so then a of 1 is going to be, so now a of 1 equals x. And now what I'm going to do is I'm just going to do the whole thing over again. And the idea here is, so for example, in this operation, we're going to be setting a of 2 to a of 2 and a of 1, which is a of 2 and x, because a of 1 is now x. And we know that a of 2 and x is just x, and so this is setting a of 2 to x. And so afterwards, all elements of the array are going to equal x, and so the maximum element is x, and so we have achieved what we're trying to do. Raja asks, are submasks and bitmasks the same thing? Not exactly. A bitmask is, it's a more general term. A bitmask is basically a way of referring to a binary number, and a submask is referring to a specific relationship between binary numbers, where A is a submask of B if the bits in A are a subset of the bits in B. Okay. Yeah, so that's a problem. I think the easiest way to do this is honestly just to conjecture that the answer is going to be the AND of all, or going to be the AND of all these numbers and then proof by AC. But I also would encourage you not to get bogged down in the formal proof. The important idea is to think about, say, okay, the answer is probably going to be the AND of all the numbers, and and at that point, then we can achieve it by this construction. Someone that says, I don't really understand how one arrives at this conjecture in the first place. It never occurred to me that the solution might be the bitwise AND of all the elements. Yeah, so this is a great question. It's a great thing to think about. I think there are a couple of things that pointed me to this conjecture. One of them is that this is a div2a. So typically, either if there's a fancy algorithm you're going to need to run, it's going to be pretty obvious, and otherwise the answer is probably some simple mathematical combination of the inputs. And so bitwise AND of all the elements is definitely a simple way to mathematically combine the inputs, and so it's something that makes sense as a possible answer. Another way to think about it is by thinking about thinking about this step. And in particular, we can see that the bitwise and of all, and that the answer is never going to be less than the bitwise and. And so then whenever you have like a pretty simple lower bound like that you can derive pretty easily, a logical next step is to think about whether we can actually achieve that bound consistently, whether we can actually get the answer down to x every time. And so that might lead you to make this conjecture, and then you'll find you can. So I think proving that x is the best possible, is that like the answer will never be better than x or better than the bitwise and of all elements, is a good way to sort of conjecture that maybe this actually is the answer. Okay. So someone said, yeah, Purple Crayon says the same thing. The way I came up with the conjecture is that the bitwise and of all numbers is an obvious lower bound and it seems achievable. Yeah. All right. Someone asked, is problem D1 and O of n cubed all right? I'll talk about D1 later, but I didn't submit an n cubed solution, but my sense is no, because n is up to 1,000. In practice, it may be that like you can submit a n cubed solution and it'll manage to pass, but I don't think it's super likely. Okay, let's talk about B. So we've got n squares arranged in a row, each of which can be painted red or blue. Among these squares, some have been painted already, and the others are blank. And we can decide which color to paint on each blank square. Our goal is to minimize the number of pairs of adjacent squares that share the same color by replacing the question marks with B's and R's. Okay, so let's think so in problems like this, a lot of time it can be helpful to think about a special case, or to think about one specific situation in which it's easy to figure out what we should do. And in this case, a situation where it's easy to figure out what to do is what happens if we have a question mark next to a cell that has already been painted. So for example, what happens if we have B question mark and then some other stuff, or R question mark and then some other stuff? And then what I'm going to claim is that if a question mark is next to a cell that has already been painted, we should paint that question mark in the opposite color. And the idea here is, and the proof of this is pretty simple. The idea is that so let's say we have B question mark and then saying, if we take BR, then we're going to have 0, that's going to cost us 0 imperfections. And it's possible that R is going to end up being the same as our next element over here. But even then, that's only going to add at most 1 imperfection. So in this case, this question mark here contributes 0, or at most 1 imperfection. Now what if we put the same value in? Then we're definitely going to have an imperfection here, because these two elements are the same. And we might even have one here if this next element is a B. So here this is going to contribute at least 1 imperfection, maybe 2. And so there's never a case where we get fewer imperfections this way than this way. And so we should always paint the elements this way. We should always paint them different from whatever is next to them, for whatever known element is next to them. All right. And so you might think, okay, well maybe this isn't super helpful here because, so let's look at the sample case, question mark R, question mark, question mark, question mark, BR. Because that tells us what we should do with this question mark, with this one, and with this one. But how do we know what to do with this one in the middle? And it's simple. What we realize that once we fill all of these values in, we're going to know what to do with this one. And more generally, if we have a configuration like B question mark, question mark, question mark, question mark, well, we know what to do with this because it's next to a B, we should make it an R. Well, now this one's next to an R, so we can make it a B. So we can make this one an R and this one a B and so on. And so what we can do is more generally, what we can do is we can just sweep left to right and place all the question marks different from whatever the letter to their left is. So for example, in the first sample test case, we would change this to a B, this to an R, and this to a B. And this does create an imperfection because there's this B on the right, but we prove that we can't do better, so we don't have to worry about that. And then the one edge case to deal with is that there might be some question marks to the left of the first letter, and so we're going to replace that with a B, and we're done. The one other edge case we have to deal with is if there are all question marks. And in this case, the idea is that it really doesn't matter whether this first one is a B or an R, just because of symmetry. So then we can just, well, I guess actually one way you can think about this is we can just do like BR, 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 and we're gonna have no imperfections, so that's clearly optimal. All right. Yeah, and Dev asks, is there any case where you just have question marks? Yeah, there is. Oh, Shania asks, are you going to show actual code? Yeah, sorry, I forgot to show you my code for A. So it's pretty simple. I just read in the input, and then I take A of 0 and equals A of I for all I, and then I just print out A of 0. Okay. Yeah, so pretty straightforward. For B, I'll show you my code now. This is a little more involved. So the first thing I do is I find the position of the first question mark. So I iterate through the elements from 0 to n, and if it's not I find the position of the first letter. And if it's not a letter, then I set the P to I, and then I break. Now, if P equals -1, then we haven't found any letters. It's just a bunch of question marks. So here I just alternate B and R by printing B when I is odd and R when I is even. Otherwise, from here, the first thing I do is I set the elements before P, and this represents, for example, in this case, this first loop represents setting these 3 elements. So for each element, if the thing to its right is a B, then I set this to an R. Otherwise, if the thing to its right is an R, then I set it to a B. And similarly, for the things to the left of the first question mark, first of all, I just don't modify anything that isn't a question mark. But then if the last one's a B, I make it an R. If the last one's an R, I make it a B. And then I just print out the answer. Oh, someone says, can you zoom a little on the code? Yeah, let me increase my font size. Sorry. Yeah, I like to use 16 point on my streams to make it nice and legible. Okay, perfect. Hopefully you should be able to see it better now. Oh, whoops. Okay. Any questions about this one? And then next we can move on to C, which I think a lot of people had questions about C and D, so it'll be good to get going towards those problems. All right. Let's see, is Codeforces up now? It is. Wonderful. Okay, next problem, Mocha and hiking. So we have a, okay, I've seen a couple of people mentioning topological sort solutions to this problem, but it turns out you can actually do something a little bit simpler. So let me explain the problem statement first. We have n plus 1 villages and 2n-1 directed roads. There are 2 kinds of roads. First of all, we just have a path from village 1 to village n that goes 1, 2, 3, 4 all the way up to n. Alternatively, and then secondly, there's a road from village I to village n plus 1 for all I from 1 to n, and we're given whether that's a road from I to n or to n plus 1 or a road from n plus 1 to I. And we have to find a path that visits all of the villages exactly once. Okay. So let me go to my notes. So the first thing to notice is that clearly we can construct a path like 1, 2, 3 up to n, just using this first kind of road. And so we can immediately get like 1 to n, and so we need to figure out whether, so what we need to think about is to figure out where does n plus 1 fit in. Now there's sort of two steps here, and there's 2 ways to motivate this. What I'll share with you the first way I thought about this problem, and then I'll show you another way to motivate the solution too. All right. So the way I thought about this is, when can we just like squeeze n plus 1 into the middle? So when can we do like 1, 2, 3 or 3 n plus 1, 4, 5 n? And the answer is there needs to be an edge. And so more generally, let's say we're trying to do like 1, 2, x n plus 1, and then go back to x plus 1 up to n. And the answer is there has to be an edge from x to n plus 1, and from n plus 1 to x plus 1. Or alternatively, a sub x has to equal 0, and a sub x plus 1 has to equal 1. And so if a sub x is 0 and a sub x plus 1 is 1 for all, or for any x, then we have a solution. So now we just need to think about the cases where, this doesn't exist. And it turns out that if there's no path along these lines, or if there's no pair along these lines, then the array A has to look something like 1, 1, 1, 1, 0, 0, 0, 0. Or in general, A is a block of 1s, possibly empty, followed by a block of 0s, possibly empty. And the reason is that we can show that if there's a 0 in A anywhere before a 1, we can prove, and I'll leave this as an exercise, we can prove that there will be a 0, 1 somewhere in A. And this is actually like a fairly common trick when you're looking at binary arrays. Okay. So what we know from this is that we're going to have either a of 0 equals 1, a of n minus 1 equals 0, or both. And the reason that we can't confidently say both is that a could just be 0, 0, 0, 0, or 1, 1, 1, 1. And if it's zeros, and if it's all zeros, then a of 0 isn't 1. If it's all 1s, a of n minus 1 isn't 0. So let's think about these special cases. So first of all, if a of 0 is equal to 1, then there's an edge n plus 1 to 0. And we know that there's I've been doing this 1 index, so let me do it like this. Okay, so there's an edge n plus 1 to 1. And we already know we can get from 1 to n, so we can just do n plus 1, 1, 2, 3, up to n. So that handles this case. And if a of n is 0, then there's an edge from n to n plus 1. So we can do 1, 2, 3, 4, and n plus 1. And that handles all the cases. So notice that there is a solution. So this idea about how the answer might not exist was actually bait. I think more often than not, if they don't give you an answer, if they don't give you a sample case where the answer doesn't exist, then not always, but a lot of the time, the answer just always exists. Okay. Now, so for me, the motivation was sort of thinking about when we can just sort of slip n plus 1 in the middle here. The other way you could get to the same solution is if you started by thinking about the edge cases. So you could think about, like, when can we put n plus 1 at the beginning? And that's when a of 1 is 1. And when can you put n plus 1 at the end? That's when a of n is 0. So then you know that, if this doesn't work, then you know that a of 1 is 0 and a of n is 1. And by the same logic as before, this means there's a 0, 1 somewhere in A. And then if you think about how can we use that, then you get to the same construction up here. Oh, whoops. Okay. So I can show you my code here. So the first thing I do is I check for a 0, 1, and if so, I print out the numbers up to position I, then I print out n plus 1, and then I print out the ones after I. So this is the case where I put n plus 1 in the middle. If a of 0 is 1, then I do n plus 1 and then 1 through n. And if a of n minus, if a of n minus 1 or a of n when we're 1 indexing is is 0, which happens in the other case, then I print out 1 to n plus 1. All right, great. Yeah, so that's all for this problem. If there are any questions, I'll be happy to answer them. But otherwise, we can move on to problem D. Okay. Now, I'll stop for a moment to talk a little about my strategy for this contest.
So when I read problem D, I didn't immediately know how to solve it. I didn't really have any great ideas. I thought it might take a while. And because I knew that problem D in total was worth 3,000 points between D1 and D2, and E was also worth 3,000 points, I realized E might not be much harder, and I ended up looking at E. And so I ended up looking at E, and I realized that the trick behind E is something that I've seen before and I'm fairly comfortable using. So I ended up doing E before D, and that significantly improved my penalty time. So the moral of the story is, if there are two problems with relatively similar scores next to each other, you should always look at both before deciding to solve one, because you want to do the easier one first, or the easier one for you. But and the other advantage of doing E first is that by the time I solved E, I was able to realize that a bunch of people had D1, but very few people had D2. And so that told me, okay, I should think about D1 first because it really is much easier. Whereas sometimes there's these sorts of subtask problems where the two subtasks are very similar difficulty. And so it's actually really helpful to know whether implementing D1 first is a good idea. All right, so D is a pretty long problem. I actually think D2 is significantly harder than E. So let's go ahead and get to it. We have Mocha and Diana, both of whom have forests with n vertices, and we want to add some edges such that after we add the edges, or so that they're adding the same edges, and afterwards both their graphs are still forests, and we want to add as many vertices as possible. Okay, so this is the tricky problem, and in particular, it's hard to sort of figure out what to do just to start. But what I did is, and so when that happens, a good first thing to do is to just write down stuff that feels obvious. And in this case, the obvious idea that I had, or I shouldn't say obvious, but like sort of the immediate bound I came up with was that the answer is at most n-1 minus the maximum of m1 and m2. And the reason for this is that a forest of n vertices has at most n-1 edges, and that's in the case where there's just one connected component. Therefore, so Mocha's forest can have at most n-1 edges, and since it already has m1 edges, we can add at most n-1 minus m1. Similarly, we can add at most n-1 minus m2 edges. So that's why the answer is at most n-1 minus the maximum here. Now, the next claim, or now, the key claim, or now, I played around with a few sample graphs, and what I conjectured was that this answer is actually always achievable. And I'll prove that to you now. So let's just number the, or actually here, let me write this. So claim n-1 minus maximum m1, m2 is always achievable. And in particular, we can do so just by arbitrarily adding valid edges to the graph. And this claim follows immediately from the fact that this is always achievable, because if it's always achievable, then that means that no matter what edge we add, it's still going to be achievable afterwards. Okay, so let's number the components in Mocha's and Diana's forest. Consider a vertex V, and suppose V is in Mocha's component 1 and Diana's component 1. And so then, okay, actually, hold on, sorry. So let's suppose for contradiction that we have a graph, or that we have a situation where we cannot add any more edges, but both
graphs currently have fewer than n-1 edges. Because our goal is just to say, all right, if either graph has fewer than n-1 edges, then we can add another edge. So then we can't add a new edge from V, which means that every vertex except V must be in either Mocha's component 1 or Diana's component 1. And so what I mean here is that we're saying, okay, let's say we can't add any more edges, so that means any vertex that we add to V is going to create a cycle. So it's going to connect us to another vertex in the same connected component in one of our graphs. So that means that every vertex outside Mocha's component 1 is in Diana's component 1. But then some vertex in Mocha's component 1 has to be outside Diana's component 1, because otherwise every vertex would be in Diana's component 1, so Diana would have n-1 edges. And what we can do is we can connect this vertex to any vertex outside Mocha's component 1, because then this vertex will be in Mocha's component 1 and the other vertex won't be, so it'll be a valid edge for Mocha's graph. And this vertex will be outside Diana's component 1, while the other one will be in Diana's component 1, so it's going to be valid too. So an edge can be added, giving us our contradiction and proving our claim. Now, someone mentioned in the chat that they just guessed at this claim because it looked correct. That is what I did too during the contest. And in particular, my strategy here was that I thought it might take some time to write the proof, and I also felt like writing the code for this claim to test this claim would be pretty straightforward. So I just so what I did is I just implemented a version of the code that was based on this claim, and I ended up getting a C. And that was really helpful. It saved me a lot of time, because then I was able to look at D2, knowing that I could just focus on optimizing my code for using this graph theory claim, rather than having to think about like what the actual correct conjecture was. But let's talk about how you can actually go from here to some code. So what we realize is we can just arbitrarily add valid edges. And so an immediate guess would be we can maintain the true forests using a DSU, disjoint set union, which if you aren't familiar with, I would encourage you to learn some more about it before solving this problem. I think there's some good articles about it on cpalgorithms.com. But DSU is pretty critical for any problem where we're looking at connected components. So we're going to maintain the true forest using two DSUs, then repeat it, and then we can just repeatedly find two vertices that can be connected without creating a cycle, and connect them. And this would be correct, but the problem is we can add up to O of n edges, and we have to check O of n squared per pairs of vertices. So this is O of n cubed, and since n is up to 1,000, this is too slow. But the idea here is, you should realize that we only need to check every pair of vertices once. And the reason is that if it's impossible to add suppose that the edge VU would create a cycle, then we don't need to go back and check VU again after adding more other edges, because adding more edges isn't going to make this stop being a cycle. So we can just iterate over each pair of vertices and add an edge if possible. And so it turns out the simplest possible greedy algorithm is enough to get a C. Again, I think the strategically correct thing to do here is to just implement this without formally proving it, unless you are very smart and the proof just comes immediately to you. But I think once you can draw a few cases on paper and convince yourself that it's probably right, this is the sort of thing where it's worth just giving it a go, because if you get WA, you're out 50 points, but that's not really the end of the world. And the complexity here is now just O of n squared. Someone mentioned n squared log n, and that would be the case if your DSU wasn't quite fully optimized. But using path compression and union by rank, DSU is effectively O of 1. So this is just O of n squared. And the other nice thing is that the code is really simple. So I use A as the DSU for Mocha and B as the DSU for Diana. I build the DSUs, and then I iterate over every pair. And if they're in different components in both graphs, I unify them and add this edge to the answer. Very straightforward. Let's see. Someone asked someone back, how old are participants of the contest generally? It's my first time participating and I'm in high school. I would say that most it depends on the country actually, because I think in the US where I'm from, it's much more common for people to start in high school and then some of them will just continue in college. While in a lot of places it's a much bigger deal in college because companies in various countries use programming contests for recruiting purposes. But in general, I would say it's mostly high school and college students, some with like some middle schoolers and some older people thrown in the mix. Let's see, any other questions? Yeah, unfortunately, I haven't really gotten a chance to do a whole lot of visualizations with using my tablet, but I feel like this just didn't turn out to be a contest where a whole lot of visualizations ended up working out all that well. In particular, I felt like I drew a bunch of graphs for this problem on my paper while I was solving it, but none of them really directly pointed out the proof of this conjecture. Mostly, I just sort of drew a bunch of graphs and I was able to achieve this answer, but none of them really pointed out how I could do so or why I could always do so. So it wasn't really the type of contest where looking at examples ended up functionally solving the problem. Someone tell me what the name of the editor on the right side is. I'm assuming you're referring to the one I'm using to write my code. And this is Vim in my Windows subsystem for Linux setup. If you're interested in learning more, I have a video called My Competitive Programming Setup that discusses this in detail. If you're curious about this one, this is Notepad++. But let's see. There's another question. Do you think @coder problems are better than Codeforces? I actually like Codeforces problems better. And the reason is that on Codeforces there are fewer problems where whether you get them I guess on Codeforces the problems just generally feel a little more motivated, and that there's a more direct path to the answer where you can say, okay, when you see this problem, you should immediately be thinking of this type of idea, and then that gets you to the answer. And on @coder, I feel like there are a lot of problems where I'm just sort of stumbling around in the dark until I just happen upon the correct solution, which isn't really as satisfying to me. I know that's a bit of a hot take. I know there are a lot of people who like @coder significantly better than Codeforces, but it's a matter of opinions. Someone asked, are there a lot of middle school competitive programmers in the USA? No, I mean, there are some, but there aren't really that many. Someone asked, how do you practice code faster? I would say it's probably not necessarily worth focusing specifically on being fast. In general, it's much more important to write correct code the first time than it is to type it quickly, because in general, debugging it can be a huge time sink. In general, you'll get faster just as you practice, so it's sort of just a natural process and not something that I would recommend focusing on too actively. Okay, so let's talk about D2. Now here, we've sort of finished all the graph theory. We know that we can we can just repeatedly add valid edges until we're done. So what we need to do is we just need to make all of our observations more efficient. Okay. So there are a few claims that are important here, and so I'm going to go ahead and So I'm going to go ahead and show you those. So first of all, let's say vertex V is in a connected component of size A in Mocha's forest and size B in Diana's forest. Then we only, or then we'll only need to check the minimum of A and n minus B vertices to find a valid, or to find a vertex U that can be connected to V if one exists. And the proof here is we can iterate over the n minus b vertices not connected to, or not outside of component B in Diana's forest. And then all of these vertices will be in a distinct component in Diana's forest, and we'll skip at most A that are in the same component in Mocha's forest. So this means we iterate over at most min of A and minus B vertices in total. And I'm going to use that in a moment to get you guys a more efficient, or to get you guys an efficient solution. But again, this is sort of a situation where you just write things down until you get something useful. Here, the motivation for doing this is that the motivation for for making this observation is that I'm thinking, okay, so suppose that that Mocha's forest contains I-connected components. Then the smallest connected component has at most n over I vertices. And so what I'm thinking is that we can use this bound by picking a vertex V in the smallest component, in the smallest connected component, and that way we'll just need to iterate over the sum of n over I vertices, which is O of n log n by the harmonic sum. In general, the sum of n over I from 1 to n is O of n log n. That's a very useful bound that you should definitely know. Alright, so that's sort of the motivation for this step, but there's one thing to worry about, which is what if there are no valid edges including V? So what if we perform this min of A and minus B steps and it's just a waste of time? So let's do the second observation. Let's say V is in component X in Mocha's forest and component Y in Diana's forest. Then the number of vertices that cannot be connected to V is equal to the size of component X minus the size, or plus the size of component Y, minus the number of vertices in both component X and component Y. And the reason is that V cannot be connected to X or to anything in component X. It can't be connected to anything in component Y. But here we're double counting the vertices in both components, so we have to subtract this out at the end. So we can only look at vertices V where this number is at most or is less than n, because then there's at least one valid option. And moreover, the proof of this observation here shows that when we pick our component of size A in Mocha's graph, there will be a vertex in that component that can from which we can make an edge. And so what that tells us is that So we can put all this together to get the following solution. So first, until we've added n minus 1 minus max of m1, m2 edges. First, pick the smallest component in Mocha's graph. Pick a vertex in this component satisfying our size of x plus size of y minus size of x minus y is less than n. Find a vertex, or find a compatible vertex in Diana's graph and connect them. Now, the code is pretty convoluted, unfortunately. So I'll show you. First of all, I make a bunch of modifications to my DSU. So first of all, I include I need the set of it mems, short for members. And mems is going to store the number of the members of each connected component. And so I'm going to merge them using small to large merging, which has complexity O of n log squared n. The second modification I make is I add this set clumps, which stores the just a set of components. So it stores like which values are roots in the DSU. Finally, I have this priority queue small, which stores the smallest connected components with their sizes. The other thing I'm going to do is I'm going to maintain this map CNT, which stores the number of where CNT of xy is the number of vertices in comp x of Mocha's graph and comp y of Diana's graph. And in order to maintain that, what I'm going to do is whenever I switch the component of a vertex, I'm going to push it to this vector to update, and then I'm going to update it later. Okay. So, as before, I build the DSU. These lines I thought I was going to need, but I don't. So I build the DSU, and then what I do is I find the current connected components for each vertex, and I store those counts. And so then what I do is, while there's a connected component in A that we haven't processed, the first thing I do is I find the smallest connected component in A. And for all members of A, and for all members of that connected component, I check, okay, is there a valid edge here? And if so, and if not, then I say, okay, I'm gonna erase this from the members of A because we don't need to check, I'm gonna erase this from the members of our component because we don't need to deal with it anymore. Otherwise, what I'm going to do is I'm going to iterate through the components of B, except for the ones that are the same as the vertex A. And that's so that we don't, that's so that we skip over the ones in the same component in Diana's graph. Then I'm going to iterate over the members of our component in B, and once I find one that's in a different component in A, I'm going to connect those. And in order to do that, I first clear the set of vertices we need to update because that's going to be modified by these two operations. Then for each vertex that we need to update, I update it by decreasing the count for its past values and increasing the count for its new connected components, and then I add this to the answer. And here I say, okay, if we've gotten through this entire component without finding a valid edge, then let's remove it from the queue. And then I just output my answer. Neil asks, what was your D2 resubmit? So I'll show you my D1 or my code. Let's see. Oh, lightning. Hopefully there isn't a power outage. Anyway, so I can't remember. So I think my resubmit was when I added this CNT or the CNT array, and when I basically started skipping bad vertices, because otherwise I haven't proven that my old submission could TLE, but I was worried about it, and so I wanted to resubmit something where I could prove it wouldn't TLE. And in order to do that, I had to start skipping vertices that wouldn't work, because the issue with my proof here, with my bound here, is that it no longer holds if it's a possibility that we might be iterating over some vertices that where there's no chance that we can find an edge connecting them that we can add. And so my resubmission reduced the search space by adding this check to ensure that we were never going to TLE. So yeah, that's why I resubmitted. Luckily, it ended up not affecting my rank, so I don't really have any regrets about it, but that's what I was doing. Turned out my first one passed pre-test, so I'll need to resubmit it afterwards to see if it passed system tests. I don't have a proof that there's like a test that breaks my old submission. It was just something I was kind of worried about. Yeah, I do think D2 was harder than E. It was a tricky problem, and there's a lot involved, but eventually it ended up working out. All right, so let's look at problem E. We want to count the number of sequences such that a sub I is an integer in the range L sub I to R sub I for all I. The sum of a sub I is less than or equal to m, and the GCD of all the a sub I is 1. And we have to figure out how many, how many of those sequences exist. Now, the prerequisite knowledge for this problem is something that's called Mobius inversion. And in general, there are a couple of number theory related sort of problem formulations where this technique can be useful. But the most common one is where we want to count the number of sequences satisfying some condition with GCD 1, which of course is exactly what we're asked to do in this problem. So what this relies on is we have this tool called the Mobius function, and the Mobius function is defined as it's called can't remember what this Greek letter is. Let me check. It's called mu. So but I don't have. Actually, no, I've copied and pasted it. Okay, so for all n, mu of n is equal to 1 if n is not divisible by any perfect squares and it has an even number of prime factors. Mu of n, the case where mu of n is -1, is the same except odd number of prime factors, and mu of n is 0 if n is divisible by a square. And the reason this function is useful, I'm not going to go into the proof, but it's actually really similar to the principle of inclusion and exclusion. But the reason that this is helpful is that then let's let f of n be the number of sequences where, or the number of valid sequences where all elements are divisible by, so now we're not asking, so now we don't need the GCD to be 1, we just need them to be divisible by whatever. They're going to be divisible by n. Then the number of sequences with GCD 1 is the sum of mu of n times f of n. Okay, so that's the Mobius function. I have a template to compute it, and so now what we've reduced this to is we need to count the number of valid sequences where all elements are divisible by n for all possible n. And so the first thing I'm going to do is I'm just going to reduce this to the case where n is equal to 1. So what I'm going to do is for each L sub I and R sub I, I'm going to compute the and actually I'm actually going to replace this with x just so that just because there's already n in the problem statement. So first I'm going to compute the smallest and greatest multiples of x in this interval, then divide them by x, and then also I'll divide m by x. The other thing I'm going to do is so that transforms L sub I and R sub I so that now we can pick any integer in the range. But next I'm going to subtract L sub I, I'm going to transform the interval L sub I, R sub I into 0 R sub I minus L sub I, and subtract L sub I from M. And so that means we're adding an integer in the range, or in a range starting with 0. And this isn't strictly required. It just made the coding a little easier for me. All right. So now we've reduced the problem to given n intervals of the form 0, let's say, to k sub I. Count the number of sequences summing to at most m. And what I'm going to do here is I'm going to do dp. So let's let dp of I of j be the number of ways to use the first I sequences to achieve sum j. And then the answer is the sum of dp of n of I over I from 0 to m. Now, naively, this dp would be O of nm squared. And the reason is that if you check is that this interval can have length m, so there are m possible values you might need to check for each position. But we can optimize this using prefix sums. And so the idea is that dp of I of j is going to be equal to dp of I of j minus 1 minus, we're not going to be able to, or minus, we can no longer add the value of position j minus k minus 1, but now we can take the value of position j. And so this lets us handle each transition, and meanwhile we know dp of I of 0 is just equal to dp of I minus 1 of 0. And so now we can handle the transitions in O of 1. So this is O of nm, or more formally for each case, it's O of n. I've used so many letters. Let's call it O of n z. Or I guess it's O of nm over x, because here we've divided m by x. Now, this is another harmonic series thing, in that the sum of m over x over all x from 1 to m is m log m. So our complexity is actually O of nm log m. And now I'll walk you through my code. So the first thing I do is I just run my Mobius function template. And then next I read an ln_r, and then I iterate over x. And so the first thing I do is I'm going to maintain the sum of the L of i's, and then this cap is going to store the values k that I talked about earlier, the values r minus l. So this does a little bit of math to get low val and high val, which are the lowest and highest multiples of x. And in particular, if there's no possible value of x that's in the range, or multiple of x in the range L of I to R of I, then I just quit. So then I'm going to add the low value to low sum and update our cap array. So now the total value we need to create is m over x minus the low sum, because we're sort of assuming the low sum is already in there. And if we need to create a negative value, that's going to be impossible. And otherwise, I just do this dp. So I maintain this prefix sum, and I add dp of I of j, and subtract out dp of I of j minus k afterwards. Luisa asks, is there any upper bound for the number of x where mu of x is not equal to 0? Yes, but for our purposes, it's not very helpful. If I recall correctly, mu of x is equal to 0, or is going to be non-zero for pi, or for 6 over pi squared of numbers. Really weird bound, not the sort of thing where you would expect pi to show up. But yeah, let me make sure that this is right, but I think, yeah, it's yeah, so yeah, it is about 6 over pi squared numbers have mu to be non-zero. And so basically skipping the ones where mu is 0 would be a bit of a constant factor optimization, but in practice it wouldn't really help all that much for getting TLE code to get AC. All right, Some people asked a while back, and I forgot to answer, but some people asked if a randomized solution could pass for D2. I'm not sure. I wouldn't rule it out, but you need to convince me that like there are going to be enough valid edges that it's going to work out. Someone asked, can you replay this video after the live stream? Yes. And someone asked, can you explain the Mobius function briefly? So I did that up here. So I'll put a link in the chat with some information that might be helpful. But otherwise, I want to make sure that we have time to move on to the CodeChef problems. So I'm not going to spend too much more time talking about it right now. Okay, and someone asked why Neil's solution is sufficiently likely to generate a good edge. I haven't looked at Neil's solution, and it probably would take me a decent amount of time to follow everything. So so for now, I can't really comment on. For now, I can't really comment on why this works. Okay, so yeah, that's a Codeforces round. Pretty fun contest, I thought. So it says, can I share my new vimrc file? Yeah, I'm going to make a video on that sometime soon. I don't want to yet because I might need to do a bit of editing to clean it up before it makes sense to share it publicly. But anyway, so once the Codeforces round ended, I ended up moving over and solving the problems on the CodeChef contest. And so I thought some of you guys might be interested in the solutions to those. So I'm going to go ahead and talk you through them. Okay, so CodeChef Starters 8. The first problem is penalty shots. So each team has 5 shots, and we're given 10 integers where the odd integers represent the shots by Team 1 and the even integers represent the shots made by Team 2. We need to find the winner or determine if the game ends in a draw. This is a pretty straightforward implementation problem. What I'm going to do is I'm going to maintain C and T, where C and T of 0 is the score of the first team, and C and T of 1 is the score of the second. Then I'm going to read in the outcome of each goal, and I'm going to add it to the score of team I mod 2, which is just a nice way to clean it up. And then I'm going to compare C and T and print out the answer. I see someone's been asking, how do you improve in problem solving, or how do you become a candidate master? I might talk about those questions a little bit at the end, but for now I want to get through the problems because that's something that's going to take a bit more time to address. So stick around if you're interested in hearing about that, and I'll talk a little about it once I'm finished going over the problems. Okay, so the next problem is javelin qualification. We've got N players who are competing in a javelin competition. We are given the longest distance that each of the N players threw. And if any player who threw at least M centimeters will advance to the final round. But if fewer than X players have qualified, then we'll continue to fill more slots until there are X participants in the finals. We have to find the list of the players who qualify. So again, this is a bit of an implementation problem. The idea here is, so first of all, I'm just going to make a list of all of the players who throw at least M units. And so then if that answer has size greater than or equal to X, then we're done, because then we don't need to go with this step. But if there are fewer than X players, then what I'm going to do is I'm just going to clear the list entirely, and I'm just going to make a list of the best X players. So what I'm going to do is I'm going to use pairs to sort the players in decreasing order of their score. And then I'm going to keep adding players until, first of all, we've added more than X players, and secondly, the current player we're looking at scores a lower number of points than the last player. And the reason that this condition is important is suppose we want to take 2 players and the scores are 1, 1, 1. Then we're going to need to take all 3, because it wasn't super clear in the problem statement. But the intent was that you were supposed to take everyone who tied for the position of the top X. So you want to make sure you take all 3 of these rather than just 2 of them. So yeah, that's how we get to this. So can you make a video on black box technique? I wouldn't really describe that as a specific technique. At least is the way I'm familiar with that term is that it basically just refers to when people just use just write templates for data structures like, you know, a segment tree or maybe algorithms like MaxFlow, and then they just copy them into problems rather than like writing them on the spot. But yeah, I don't really have any plans to make a video about my templates, largely because most of my templates are not written by me, and so I don't want to take credit for stuff that mostly was written by other people. All right. So the next problem is 3 points. We're given 3 distinct points in the XY plane. Initially, we're going to start at point A, and we want to reach point C while going through point B and while making at most one 90-degree turn. Okay, so finally, this is a problem where it's going to be helpful to draw things. So let's think about when this is going to be impossible. Now, obviously, if we're going to need, first of all, realize that we can go from one point to another while making at most one turn every time. So for example, if we have A here and B here, we can do something along these lines. But then if we need to make a turn from A to B and another turn from B to C, then the answer is no. So then we need to think about when we need to make a turn. And the idea is that if A and B are on the same horizontal or vertical line, then there's no need to make a turn. We can just go straight. So for example, if B is on the horizontal line, then it looks like that, and we don't need to turn. If it's on the same vertical line, we also don't need to turn. So in general, no turn if XA equals XB or YA equals YB. Okay. So if that's the case, then we're only going to need to make one. Then we're only going to need to make one turn. Now the other catch is that we're going to need, or is that we need to is that we cannot reverse course. And what I mean by that is that well, here, I'll show you. So if we have A here and B here, then we can't have C back here, because that would require us to, actually, hold on, sorry, this is a bad example. So if we have A here and B here, then we're going to need to have C somewhere in this region, somewhere past B. And the reason is that in order to get if C were here, then we would need to make 2 turns. Or even if C were on this line back here, we would need to make 2 turns because it costs us 2 turns to make a 180. So in general, if we have to go in a certain direction to get to B, so like if we have to increase X to get to B, then we can't decrease X to get to C. And it turns out that we can show that these conditions are sufficient. So as long as we only have to make 1 turn, and as long as we don't have to reverse ourselves, then we're good. So I'll show you how I implemented this. I think I did this in file E. Yeah. So first of all, I implemented this code reverse, where I'm saying, okay, if we have the X coordinates, X, Y, and Z, then if we're increasing from X to Y, but then decreasing back to Z, or if we're decreasing from X to Y and then increasing from Y to Z, then there's a reversal. So this returns true. And the other thing I do is I implement a function about whether we're going to have to turn on the path from XY to AB. And this is the case if x is not equal to a and y is not equal to b. So then I say, okay, if we don't have to turn from a to b, and we don't have to turn from b to c, and then if our x coordinates don't reverse and our y coordinates don't reverse, then the answer is yes. But if either of those conditions aren't satisfied, the answer is no. All right, next problem. So the problem is called square function. We define a function f of x to be x over y, where y is the largest perfect square that divides x. We're given an array A consisting of n integers, and a pair of integers is called good if f of ai aj is greater than 1. We need to find the number of good pairs. It turns out here that it's actually really easy to think about, or that it helps to think about when f of ai aj is going to equal 1. And so this is the case when so f of this is going to equal a sub I, a sub j over y. So that means that whenever f of x is going, or whenever f of this thing is 1, we're going to have y equals a sub I, or not plus, sorry, a sub I, a sub j. And what this tells us is that f of ai aj is going to be 1 when a sub I, a sub j is a perfect square. So, ij is not a good pair when a sub I, a sub j is a perfect square. So now we need to count the number of pairs that are perfect squares. And this is actually a fairly standard problem. The idea here is that a sub I, a sub j is a perfect square if and only if f of a sub I is equal to f of a sub j. And the idea here is that if a sub I and a sub j have the same f value, then when we multiply them together, let's say f of a sub I is equal to a sub I over, let's say, k squared, and f of a sub j is equal to a sub j over, why am I using k? I'm going to call this x squared, over y squared. Then f of a sub I, a sub j is going to equal, or so then a sub I, a sub j is divisible by x squared y squared, because a sub I, a sub j slash x squared y squared, I know there should be parentheses here, but I'm lazy, is going to equal a sub I slash x squared times a sub j slash y squared. And if those two things are the same, then this is going to be a perfect square. And otherwise, we can show that it's not going to be a perfect square. Now, computing f of x for all input x would be too slow, since there are 10 to the 6 values of x, and up to 1,000, and since x can be up to 10 to the 6, there are 1,000 perfect squares to check. So what we can do instead is I'm going to pre-compute the value of f of x for all x up to 0, up to 10 to the 6. And I'll show you my code now. So I maintain this array value is going to store the value of f of x for all x. And the idea is I'm going to iterate over all perfect squares, and then for all possible values of f of x, I'm going to say so I'm iterating over the perfect squares I times I, and then for all j, the value of j times I is at most j. And since I'm doing this in increasing order of the perfect square, we're going to end up with the lowest. We're going to end up getting the greatest perfect square for each value. And so then, what I do is I store the number of times each value appears, each value of f of x appears, and then initially the number of good pairs, I'm just setting it equal to n choose 2, which is the number of pairs that exist in general. And then I'm going to subtract out And then for each, and then, so then I'm going to iterate over the counts, and here a dot f is the value and a dot s is the number of times it appears. And so I'm going to subtract out the number of ways to choose two elements with this value. And in that manner, I get rid of all the of all the cases where f of a sub I is equal to f of a sub j, so I'm left only with the good pairs. All right, 2 problems left. So the next problem is called closest power. Pretty straightforward problem statement. We're given an integer n up to 10 to the 18, and we need to find the closest perfect power to n. The catch is that there can be up to 10 to the 5 cases in a single file, and so the time limit turns out to be really tight. And what that means is that, and in particular, because the time limit is so tight, realize that like some of the functions we might want to call, like for example, pow, is relatively slow. So, so iterating over the powers p and finding the closest power of p, or the closest p power to n is too slow. So like for example, we might say, okay, let's find the closest square, then the closest cube, then the closest fourth power, and so on, but it turns out that that TLEs. So we're going to need to do something better. What we can do here is, so what we can do here is realize this n is up to, that like there are going to be a lot of perfect squares and even a lot of perfect cubes, but beyond that there really aren't that many fourth powers, fifth powers, etc. And in fact, I guess there really aren't that many perfect cubes either, but I digress. So what we can do is we're gonna maintain a set, or we're gonna pre-compute a set consisting of all fourth powers, fifth powers, etc. Then we're going to find the closest element to n in our set, and then also we'll directly find the closest perfect square and perfect cube to n, and that's gonna check all possible powers. So let me show you what this looks like when I implement it. So notice that if x to the fourth is going to be less than or equal to n is at most, if x to the fourth is going to be relevant, then its value is going to be at most 10 to the 18. So x to the fourth has to be less than 10 to the 18. So we only needed to consider x less than or equal to 10 to the 4.5 power, which is about 32,000. So I'm going to iterate over these values of x, and then I have these safe multiplication and exponentiation functions, which are basically just multiplication exponent functions that I've designed to prevent long overflow. And I'm just going to repeatedly, and I'm just going to add all the powers of these values to our set. Someone says 4 is irrelevant. Yeah, it is, because any fourth power is also a perfect square. But it just was a natural place to put the cutoff anyway, since like you can still account for the fourth powers and it's still not going to TLE. And then I'm going to iterate over the squares into cubes. So I is the power. So when I is 2, we're looking at perfect squares. When I is 3, we're looking at perfect cubes. Then what I'm going to do is I'm going to say, okay, suppose we're trying to find x such that x to the p is approximately n. Then x is going to approximately equal n to the 1 over p if we raise both sides to the 1 over p power. So that's how I handle this. And then I say, okay, I just check this value and this value plus 1, and I see if it works. And then I use the set powers, and I check the next greater value in POWs. And in this statement, in this conditional, I check the next lower value in powers. And so that accounts for all the cases. So then I can output the answer. Okay, and now the final problem. Okay, so we've got n people numbered from 1 to n. Each of them buys a ticket which has a number written on it. And what's going to happen is so we've got a person in the front of the queue. If their seat is empty, then they're going to get out of the queue and they're going to take that seat. Otherwise, their ticket is going to be incremented by 1 and they're going to return to the back of the queue. And we have to find the seat number occupied by each of the n people. Okay. So here's a pretty simple observation. Observe that if a person has a ticket number a sub I, then they'll never take a seat numbered less than a sub I. So they'll only take a seat greater than a sub I. And equivalently, CX will be assigned to someone with a ticket numbered lower or less than or equal to X. And what we can do with this is we can say, okay, seat 1 will be assigned to someone with ticket number 1. Seat 2 will be assigned to someone numbered 1 or 2, etc. So what I'm going to do is I'm going to assign seats in increasing order. And what we need to do is we need to add all the people with and so to assign CX, we need to add all people with tickets numbered X, and we need to figure out which of the people whose tickets are less than or equal to X and who still don't have seats get CX. And here the idea is that this is whichever person has the highest ticket number, breaking ties by whoever is first in the queue. And the reason is that the person with the higher ticket number will have to sort of go through the queue and then return to the back fewer times before getting their seat. And so I'll show you how this works on one of the sample test cases. Let's look at, what's a good one? Let's look at the first sample test case. We have 1, 2, 3, 2, 4. So initially, so when we assign seat 1, that this person is the only person who's eligible, so they get seat 1. When we assign seat 2, these 2 people are eligible. They have the same ticket number, but this person is first in the queue, so they get the seat. Now when we assign ticket 3, these 2 people are eligible. Notice that the person 2 is still eligible because they didn't get seat 2. But 3 is a higher ticket number, so they get the seat. Now, these 2 people are eligible, but 4 has a higher ticket number, they get the seat. And finally, we have seat 5. This is the only person eligible, so they get the seat. And so I'll show you how this is implemented. Okay, so I'm going to maintain a set of positions positions in the array of individuals with each ticket number, and then I'm going to iterate over the seats. And we can show that no seat greater than number 2n is going to be assigned. So that's when I stop my loop. So then what I do is for all I use a priority queue, and this PQG construction in my template means that I'm going to prioritize the smaller ones first. So then I'm going to iterate over the values at this, or all over the individuals with a given ticket number, and I'm going to add them to the queue. And so I'm sorting first by the greatest ticket number. So since our queue is looking for the smallest values, that's the smallest negative times the ticket number, and then A is the position. And then if there's someone who still hasn't received a seat, I take the first person out of the queue, and I give them the seat. So yeah, that's the problem. And that's the contest. So yeah, appreciate all of you who have stuck around so long. Sorry if some of the CodeChef explanations are going a little fast. I think
explaining 12 problems at once is kind of exhausting. I think next time I do this, I might build in a bit of buffer time between talking through the 2 contests. But hopefully these explanations were helpful. Now, as far as the person earlier who asked like for tips on how to improve, there isn't really anything. So like first of all, there isn't really any magic advice that I can give you that's going to immediately improve your Codeforces rating. It really comes down to practice. That said, in general, I endorse the practice tips that are given on Ericto's wiki, and I'll put that in the chat. I think this is largely consistent with the way that I practice. And so in general, I would say to try and solve problems that are pretty much exactly like he says, solve problems that aren't easy for you, but you should probably be eventually manage to solve them more often than not. So in general, if you're solving too many of the problems you attempt within the first like 10 or 15 minutes, then you're probably doing problems that are too easy. But if 80% of the time you can't even solve the problem at all and you have to look at the editorial, then you're solving problems that are too hard. The other thing I would say is that you should not be one of those people who like refuses to ever look at an editorial. I think in general, in certain cases, it can be really helpful to have access to editorials, as long as you make sure to learn from them so that you'd be able to solve the same problem next time. And so what I mean by that is if you don't know how to solve a problem, I would read the editorial and then I would implement the solution to make sure you really understand it. And afterwards, I would take some time to think about why you didn't solve that problem and what you're going to do to solve that problem again in the future. And so to solve a similar problem if it comes up in the future. And so, for example, if you look at problem A, and you aren't able to solve it, then maybe your thought process is, okay, the reason I didn't solve this is that I didn't solve this is that I wasn't able to guess that the answer was going to be the bitwise AND of all the elements. And the way I could have, so in order to get a problem like this in the future, the way I could have gotten this is I could have thought, okay, what's the best lower bound that I can prove obviously, and then I'm going to try and prove why that lower bound is actually achievable. So it's tricky and it's definitely an ongoing process. I certainly don't know everything at this point, but that's generally what I would recommend. And someone asked, what do you think about solving problems from Use the Code Guide for improving on CF? I mean, I think really the fact that you're doing problems matters a lot more than which specific problems you do. Having said that, I think the Use the Code Guide is a great way to learn various topics. But in Codeforces, a lot of how well you do in Codeforces rounds is really more dependent on your ability to solve these sort of ad hoc problems or to make observations, or to solve problems where it may not be obvious which topic they fit under, or they may not even fit under any particular topic at all. And so in that sense, it can be less valuable to solve problems where you already know what the topic is going to be. But basically, and so I would say while you're still learning various topics, the Use the Code Guide is a great resource for doing that. But I would probably lean towards solving problems on Codeforces or on some other platform, or even if you're just solving problems from the Use the Code itself, I would lean towards solving problems where you don't already know what the topic is before solving them. But again, focus on solving problems. Don't worry too much about which specific problems you're solving. Let's see, have I gotten AC on all my submissions? Looks like my D is the last one in the queue. Okay. Anyone else have any questions? All right, awesome. Yeah, so that's the stream. Thanks for watching, everyone. Please feel free to leave a comment if you have any follow-up questions, and I will see you